Hey, welcome back to further optimization. In this presentation, we want to look at some three-dimensional problems, like how big a cylinder can you put within a cone, or a cone within a sphere, or a cylinder within a sphere. What's the biggest size, maybe the biggest volume that you can fit in a known cone or cylinder or sphere, whatever. How about that? And you know that what we've been doing is creating a formula for the function and then using technology to find the best solution, which up here, the maximum area would be at that point there, and this would be the value of x, a variable we've introduced. So let's just review what we've been doing there before, and if you have a look, here's my hints for you. These hints for solving optimization problems. Carefully read the question. Underline key points. We'll practice this in a minute so you don't miss anything out. Draw a diagram and mark all the information on it. Now here's a key one. Introduce a pronumeral for the key quantity or variable which is missing. They say find the dimensions to give maximum area, then you want to introduce x or some letter to represent one of those dimensions. Okay, and then work on the rest of it by what? Writing a formula for the quantity to be maximised or minimised. And if there are other quantities in the formula, like not just radius perhaps, but the height of a cylinder, then you must try to write them in terms of the introduced pronumeral. In other words, work all in Xland. Don't have an R and an H. Try to get it all in terms of one variable, because you know what's going to happen if you can write it in terms of a single letter or variable. You can use algebra or technology so that you can find the maximum minimum value. But you can't enter on the calculator and take the Casio in the F1 position. You can't represent something like pi x squared for radius, h for height of the cylinder. You have to have h in terms of x. So if you're going to use technology, it's got to have a single variable there. Okay, you get it. And then state your answer in the context of the question. Don't say that x equals, you've introduced that for maybe the radius, so you have to unpack it in the context of the question. State what the radius would have to be, not the value of x. Alright, do you get the idea? Let's go and have a look. And again, we're going to go back to the Harradine and Lupton book there. And we're on question 9 here. I've left some out, but I've picked out some interesting ones. So this is a 3D problem, isn't it? Three-dimensional problem. It's a juice box, and it's going to enclose 600 centimetre cubed of liquid, and it's going to be square-based and rectangular prism. Okay. If the square base has x centimetre side lengths, let's put this in. That would be x, 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 x. And on the bottom as well. Okay, square based. All right. Now, let's say we're going to do this problem. Now, how these hints vary a bit from these steps here. So what I'd like to do is you could try this problem. You pause the presentation now and try it by doing A, B, C, and D. Or I'm going to suggest perhaps we do it slightly differently from that. We want the smallest possible total surface area of the container. So you remember my hints to you. You try to write a formula for the quantity to be maximised or minimised, or to be optimised. So can you pause the presentation and try to work out the area expression for that juice box? So pause it now and have a go. Alright, I'm back. The surface area A will be what? 2 ends, and each of those are squares. X by x is x squared. Plus, what sides? We've got 4 of these sides. Okay, the 2 sides and front and back, so we've got 4 lots of. Now, what's the area of those sides? We don't know the height, so we'll have to use an h here. That is 4 by x by h. Do you agree? That's the surface area. Now what's the next hint? It says you've got to try and get rid of all but a single variable. So I want you to look through the given information and try to get rid of h and replace it with an expression in x. Okay, pause the presentation now Okay, I'm back again. So what's the only piece of information that we haven't used? It's that the volume is 600 centimetres cubed. So let's write that down over here. Volume is 600 centimetres cubed, and the volume of a square-based or area of cross-section of x squared, square base, is area of the base times the height, isn't it? Remember that? The volume, let's lay it down this way. Remember the idea of the volume of a body of uniform cross-section. First of all, find how many squares we can get in there. So that's x squared, because it's x by x. And then if we slice it along here, 1 centimetre at a time, how many slices will we have? We'd have 8 slices. So every time you slice it, a little cube would fall off. A set of cubes would fall off, wouldn't they? So you would have 8 bundles of x squareds, and each would form a cube at every slice. So this is the number of cubes we will have. So that's where it comes from. The volume is the area of cross-section times the length, or the height of the object. Okay, so here it's x squared by h. So can we get h by itself? Yes, let's divide both sides by x squared, and you get h. Alright, so what is the calculation now, or the formula for the total surface area? Watch it now. It's 4x times 600 over x squared, if you like. And then, if we put that on the calculator or in table mode, you graph it or in table mode. Graph mode is handy because we can actually then go to shift, this is on the Casio, shift F5 gives us G-solve, and it will go along and pick out the minimum that we want here. We want the smallest, the optimal here is the smallest surface area. Well, I've just done that for you, so I'll show you in a minute, and I'd like you to put on the calculator and see what you can do. Alright, come back now and let's have a look what it looks like. Here we are here. We'll put it in graph mode. It's 2x squared plus 4x by 600 on x squared, and we've got a graph like this. Need to go fairly large for x, as you'll see in a minute, and if we then go shift and F5, which is G-solve, we get this window, and we want the minimum, so we'll hit the key below it, F3, and it pops on there. You can't actually see it's down here, but the minimum occurs when x is 8.43433, and the minimum value is, this is for the area, is 426.827, etc. Okay, not bad, is it? But we must, of course, coming back to this window over here, get the formula in terms of a single variable. X can only put one variable in there for this type of analysis. And later on, you can't do this one algebraically at this stage, but later on you could use calculus to find the minimum value without technology, and the same thing applies. You need that function in terms of a single variable. Let's check our answers now down here from Harradine and Lupton's booklet there on optimisation. So yes, h was 600 over x squared, the area was correct, and then we found it was 8.434, that's the base, and if we find the height by, the height is 600 over 8.434 squared, then it comes to another 8.434. That's interesting. So the juice box, they haven't completely done it here, is 8.434 by 8.434, and it's square based. Okay, so it's a cube. That's what we're saying. That will give you the minimum surface area. Okay, why might you want the minimum surface area? Well, anything which is cold or hot will absorb or radiate heat depending on the size of the surface area. So the bigger surface area, the hotter the contents are going to get, or cooler if they're hot and cooling down, if you know what I mean. The heat transfer is going to be greatest with the greatest surface area. So this would be the least or smallest surface area. Alright, did you like that one? Well, I've got one for you, again from the Hardeen and Lupton booklet. Here it is here, and I'm not going to do this one with you. Okay, now again, what they've asked you to do is set it up like the last one. I would suggest using my hints there. I'd like you to go to find the smallest possible surface area by starting with a formula for the surface area, then going and looking at what's given up here and seeing if you can use it so that you only get one variable, and they're saying a base radius of r, so you'll go through in R land now. Okay, see if you can do the same sort of thing. I'll pause the presentation now and have a go, and I'll come back and take you down to the answers. Right, let's go down to the answers now. There it is, that's what they reckon here the juice can would look like. How did you go? Okay, so here they are. The height is 9.142. The diameter of therefore is 9.142. Oops, hang on, we'll just go back up there. And the radius is 4.571. Okay, so do you get the idea there? I hope you can check out these expressions. You need to know some formula volumes here and surface area formulas as well. Formula for volumes and surface area to be able to get through some of this. Alright, how are you going? Study it, try to use that technique. My hints in that sort of format will solve every problem. You have to have a system here to crack the problem. Now, here's an interesting one. Cylinders within a sphere. I already showed you this back on the page. Now, with a sphere of radius 10 units. 3 examples. Can you see? They're quite different. Do you have a long, skinny one, a shorter, fatter one, or even shorter, fatter one, sort of thing? Okay, one has greater volume than all the others. What are its dimensions? What proportion of the sphere's volume does it enclose? Well, let's go about it in the same way. First of all, we better label the diagram. Now, it's got a radius of 10 units. Okay, so let's use this one in the middle. We'll just tidy this up. It's got a radius of 10 units. So there, that's 10, isn't it? And we want a radius of the cylinder. So let's make sure here. We'll just go through here. We are going to assume here that the greatest volume, assume the cylinder will be symmetrically placed, watch this now, like these diagrams, symmetrically placed in the sphere. Okay, because that's the way they've got them here, and that's how you're going to get maximum volume. I think you can see that. So if you go up there, let's draw this in, across here now, that would be the radius of the cylinder. Okay, and we want a volume, so let's go searching for a volume of a cylinder. Do you know it? Can you write it down? Have a go. Well, of course, it's a body of uniform cross-section, so it's the area of the end times the height. Right? Same idea, make all squares up here. Okay, and then as you slice through, they become cubes, and you've got 8 slots of the squares in terms of creating little cubes coming off at every slice. So the body of uniform cross-section has the formula area of the cross-section. Here's a circle, pi r squared times h. Uh-oh. Again, can you see we have another variable here, not just r, but h. I want you to pause the presentation and see if we're using this diagram you can work out h in terms of r and using the 10. Pause it and see what you can do. This is quite hard. Alright, did you get anywhere? Mostly people don't, because you need this line here. Okay, now that's 90 degrees, and this is the one you need to call 10. This is 10, sure, but it's not using the 10 in conjunction with the height, which is this thing here. But if we go through there, let's say just extract that. So I'll get rid of this here. Just extract that triangle in there. So we've got this. This would be the overall h on 2, wouldn't it? Half the overall height. This is 10, and this is the R of the cylinder. Can you see that trick? You have to work the given 10 into a position where it's in a triangle with the R and H, so we can connect them all up. Let's use Pythagoras now. Okay, I want you to pause the presentation and see if you can get an expression for H in terms of R. Alright, by Pythagoras, the square on the hypotenuse equals the sum of the squares on the other two sides. And you should put in brackets Pythag. Okay, so let's keep working. That implies 10 squared equals R squared plus 8 squared on 4. Let's try to identify or isolate the 8 squared. So let's subtract R squared from both sides. So 10 squared is 100, take R squared, equals 8 squared on 4. Multiplying both sides by 4, you've got 4 lots of 100 take R squared equals 8 squared. Which implies, let's take the root of both sides. The root of 4 is 2. Root 100 take R squared equals H. And H is greater than 0, so it's a positive root only. Please note, you cannot find the root of these two and take them away, because a square, a squared plus 2ab plus b squared, has in fact 3 terms. So this is not, you cannot simplify this at this stage. So we're going through the hints now, aren't we? We've done all the labelling, we did our formula. Now we have to get it in terms of a single variable. So it's pi r squared times 2 root 100 take r squared. Do you agree? Okay. Now once we get to that stage, we can use technology. At this stage, you cannot do it algebraically. This is approximately year 11 level. Algebraically, you can't do that. You need calculus to do that. But you could use technology. Okay, if you know calculus, have a go. But we can't do it without technology. Okay. Can you put that on your calculator now? And see if you can find the greatest volume. Let's come down and have a look at what we get. Alright, so here we are, putting in our function pi x squared. Remember, in technology land, this is on the Casio, any variable has to be designated x. You can't put in r as such. Okay, well, we don't usually anyway. Okay, so there we have it. Again, finding the maximum this time using Shift F5. We find it's when x is that and the maximum volume is that. Okay. It also says, so what are its dimensions? So the dimensions of the cylinder, let's have a look. Dimensions are, the radius is 8.16 centimetres. So that's the 3 significant figures. And its height, now what was the height? The height is 2 times the square root of 100 take r squared, 8.16 squared, and you can work that out and quote it to 3 significant figures. So you're saying that this has a certain radius and we've got a height here. Okay. We'll have a look at the answers in a minute. Okay, dimensions. Also, what proportion of the sphere's volume does it enclose? What proportion? Well, here's the volume that we've got. If we divide by the volume of a sphere, check this, volume of a sphere is 4/3 pi 10 cubed, r cubed. We don't use r because we don't want to confuse the volume, the radius of the sphere with the radius of the cylinder. So here are pi 10 cubed times by 4 divided by 3. So then if we this is in math mode, so that's the exact answer, then this is our maximum volume of our cylinder. Divide by the answer gives a proportion. So the proportion is our maximum volume divided by volume of the sphere, which is 2418.4 over pi 10 cubed times 4/3, and that's approximately 0.577 to 3 significant figures. 3 centimetres. 3 significant figures. And that's a proportion. It's a fraction of the total that this cylinder is going to occupy within the sphere. It's interesting stuff, isn't it? This three-dimensional work. You've got to get your head around the idea. Please stick to my hints in working out any formula for the quantity, then using the given information to remove all but the single variable, and then go into technology. All right, let's check the answers down here. No, I didn't have the answers there. Oh, well, not to worry. Okay, you can check those in the booklet if you like. Let's have a look at what you want to do now. Can you do one for yourself? Consider the possible right cones. So right means it's straight up and down. Right angle. The line joining the vertex to the centre of the base is at 90 to the base. In other words, it's not like this. It's not across there like that. Okay, so it's right in the middle. A right circular cone says a line from the vertex to the middle of the base is at right angles, right in the middle there, not kinked over at all. Okay, so what I want you to do is to go through and underline all the important things here. Right cones, that means a right angle, and introduce a letter, and you want the greatest volume. So the optimal solution, the best solution is greatest volume. What are its dimensions? Okay. Try to do the same sort of thing as we did before. See, can you see here the two guys have not led us through steps, so we have to know Huddy's hints here for how to do this. Okay. Make sure you use this 10 unit radius in a situation where you can relate it to the height and radius of the cone. A bit challenging, this one. Okay. Pause it, have a go, and I'll just show you the answers. So coming down here, there's the answer. Base radius and height, and that's going to be in centimetres. Okay. How did you go? Go back and check it. Alright. Let's go to a final one in 3D land. Here's another one here. Same approach. Try and stick to the same technique of problem solving with these. It will always work. Okay, pause the presentation, have a go. Okay, I'll show you the answers now. There we are. These are all in centimetres. Interesting. That's a point of discussion. You could discuss that with classmates or teachers and so on. See what you think. Alright, now I've got a couple of others from Hayes and Harris here. Publication for Year 11. And it's a slightly different one here. We've got graphs of two functions. There's the first one, and there's the second one. Prove that the graphs meet where x equals 0. So remember where they meet, these points have a common x and y. So if you put the two y expressions equal, you should be able to find that common x and y. Find the maximum vertical separation. Well, it looks like it's somewhere in here. That separation, which is what? The y on top minus the y on the bottom. And we have formulas for both of these. That gives you a few hints. Okay, have a go. Try to go through exactly the same procedure. And that is, you're trying to get that height in terms of a single variable, if you like, which will be in terms of x. Okay, pause it, have a go. I'll show you the answers now. There it is. It was only part B, finding the maximum separation is 3.125 or 3 1/8 units. One more from Hayes and Harris. There's a couple of interesting ones I picked out from there. Okay, infinitely many rectangles. There you are, there's one drawn, can be inscribed as shown. So you could have them down like that as well. Okay, so if you take this one, I'm going to illustrate that AB equals X and BC equals Y. I want you to put it on the diagram. Remember, that's the first hint. Use similar triangles to find Y in terms of X. Okay, and you want maximum area for ABCD. I would have said find a formula for the area of ABCD and then get rid of all but a single variable. Okay. Do you remember similar triangles? Similar triangles produce one from the other by enlargement. So you start at a centre of enlargement, join the first point and stretch it out in a ratio there. Let's say this is 1 unit, this is 1.5. Then each one is multiplied by 1.5. That's how you get similar triangles. So this is stretched out to this by 1.5. Okay, so that's the idea with similar triangles, because you then preserve the shape. The shape is the same, and they are equiangular, and they are properties of this stretching. So you get common ratios of all the sides, common ratios of sides. Okay, so you can use those ratios to find one missing. So try to relate that to this diagram. Good luck, and I'll pause it now and have a go with those hints, and I'm going to show you the answers. Here we are. There are the answers there, the formula, and then the final dimensions, which give ABCD the maximum area. Well, I hope you enjoyed that. You're ready to do some more optimisation in Year 12 using calculus if you've got those skills. So check it all out. I'll catch you a bit later on. Cheers for now.